formal metatheory and second abstraction. Let me stop and start.
Lovely. Thank you very much. Okay. What do you think of when you hear the words weakening, substitution, and type preservation? If you're a, I guess, classically trained pen and paper theorist, you might say, well, type preservation is the important property. It's proved by induction on the reduction relation, and you might use the substitution lemma at some point, which is this fairly straightforward inductive proof with some of these trivial structural conditions. If you're a user of proof resistance, your first initial reactions might be dread, anxiety, frustration, and just wanting to give up before you even start formalizing anything. Because you know this is not the whole picture. The whole picture is a whole pile of other, even more general definitions, some of which may seem quite arbitrary as well, and lots of extra inductions as well. And this is not even the bad part. The bad part is when you start proving properties about substitution to prove things such as the fairly standard laws of the identity substitution and associativity. You will need to go through, at the very least, 10 extra lemmas, and altogether do 6 rounds of induction on the term syntax, which for a large syntax, which may evolve quite a lot, is quite painful. So this isn't really sustainable. I hope you can all agree. And it might actually deter people from actually using proof assistance, because it seems like they just demand an intimidating amount of rigor. Sometimes this rigor is useful. Sometimes you want to help get the proof assistant to help you uncover some of these more subtle nuances of your proofs. But in this case, it's not rigor, it's boilerplate, right? This is the boring stuff that isn't really intellectually stimulating, and I don't really want to write it all over again every time I want to formalize something, but it's something I have to do. Well, maybe you don't have to do this. Maybe we can actually use a bit of automation, a bit of code generation to get enough out of our syntax so that we don't need to do any of this boilerplate manually. And that is what our system is trying to achieve. So we start with a syntax description file. This is just a textual definition of the syntax. So in this case, it's the simply type lambda calculus with the specialty they can express binding operators in it. So the lambda operator can bind a variable of type alpha to produce a function of type alpha to beta. And with a Python script, we actually generate Agda formalization code, which includes the data type of the type and terms, which is inductively given, and also the initiality proof of the syntax, which is enough to instantiate a general metatheoretic framework from which we can extract things like weakening and single variable substitution, and even denotation and interpretation functions in suitable models. And not just this, we can also extract the correctness properties of these operations entirely without any extra work on the part of the user. So in this presentation, I'm going to give you an overview of this system and how it works, beginning with the mathematical model and the library, which implements a lot of the abstract categorical notions that we make use of. So our motivating goal really was to do as much of the constructions in this category of sorted families and functions between them. So a sorted family is really just a set indexed by a type. This is the type of the source of the syntax, or the type of the syntax, and context, which is just a list of terms, a list of types, sorry. And then with the family of maps between these objects, we get a category of families, and we try to stick to this family, to this category as much as possible. And some interesting objects in this category are, for example, the family of variables, which is given in this familiar type and scope-safe De Bruyne index approach, but also the family of terms for a syntax itself. And you might recognize this as a very common way to encode syntax in dependent type proof assistance, sometimes called intrinsic encoding, where given that we have access to the type and the context of each of these arguments, we can express the typing rules of the operators as part of their signature. So you can see how the application constructor takes terms of type of function type and another term of the argument type and give you a term of the return type. And you can see the same thing with the lambda constructor, where we extend the context of the body and then turn that into a function. Another abstraction that we make use of is something we call a context map. And this is really a type-preserving mapping from a context, like gamma, to terms that live in another context. So for every variable or type in the context gamma, we give a corresponding term, all of which live in the context delta, and this gives us a mapping from variables in gamma to terms, x terms in delta. So in Agda, this is represented as a function space. So we map variables in gamma into x terms in delta. And as a special case, when x is itself the family of variables, we have this notion of a renaming. And that is really just a mapping from variables in gamma to variables in delta. And this makes the context with renamings between them a category. And this is forms a fairly fundamental part of the meta-theory that we use. And we combine these two abstractions into this idea of parameterizing a family with a context map. So we define this notion, this operator on families called the internal hom of two families, which parameterizes its second argument y with a context map of the first argument. So this might look a bit abstract, but if we consider a special case, which is when we fix the first argument of this hom to be the family of variables, and define this to be this box modality, then a term of the family box x at context gamma is going to be a function which expects a renaming from gamma to delta and give you a term in the context delta. So it's the family of renamable terms which can absorb renamings as well. And very similarly, elements of this endo hom are going to be the substitutable terms because they can expect a substitution going from every variable in context gamma to x terms in context delta. And when you apply this t to one of these sigmas, you get a term in context delta. So given that we have managed to characterize everything in terms of these objects in families, we can actually capture the notion of renaming and substitution, both as the operator itself, but also the general structure, together with its laws, as algebraic structure on sorted families. So for instance, we can show that this box modality is actually a comonad on the category of sorted families. And coalgebras for this comonad are going to be object x with a structure map going from x to box x. And if you think about what this means we are turning an x family into a family which can be further renamed with an extra renaming map. So it really is corresponding to the renaming operation. It turns objects into renamable objects. And if you spell out what this means as a set theoretic function and just do a small modification of moving this delta in the front, you can really see how this is an operation which takes an x term in gamma, a renaming from gamma to delta, and gives you a x term in delta. And to be a coalgebra for a comonad, you actually need to satisfy some laws as well, which is compatibility with the comonad structure. And these, when you once again spell them out, correspond to hopefully familiar notions and correctness properties of renaming. For example, renaming with the identity is a no-op, and doing two renamings one after the other is the same thing as doing one renaming with a composite renaming. So these are really can also be seen as the functoriality properties. If you are familiar with the pre-sheaf model, this is where kind of the pre-sheaf structure comes from. We do something very similar with the substitution structure as well, except now the algebraic notion that we are looking for is that of a monoid. And it's a slightly unusual monoid because it's a monoid in a closed category. If you consider a monoidal closed category, then a map of this form, which is a map into the internal hom, can be uncurried into a map from the tensor product m times m into m, which is then the familiar monoidal multiplication operation. But in this case, we focus on the closed structure, and define monoids in terms of this. So a monoid is therefore a object M together with a unit, which really is the variable map, and this multiplication map, the curried multiplication map, which once again corresponds to substitution, because we are turning a family into a substitutable family. So it's something which can further take a substitution mapping and modify the context accordingly. And perhaps unsurprisingly, the laws of a monoid then correspond to the familiar laws of substitution. So for example, substituting into a variable is the same thing as applying the substitution. And the other two are these correctness properties, such as mapping variables to variables is a no-op, and that substitution can be reassociated as well. In practice, we usually are more interested in the more specialized versions of these. So the single variable substitution, which in the intrinsically typed setting, its type corresponds precisely to the substitution lemma statement. It can be derived from the multiplication operation just by selecting appropriate substitution. And similarly, the associativity map, law can be specialized to the single variable associativity law as well, which is the one you might encounter more frequently in your metatheory. So by really focusing on the categorical viewpoint and focusing on the category families and trying to express everything in those terms, we have a quite natural characterization of substitution and renaming structure. So showing that a family of syntactic terms has the substitution structure, it is sufficient to show that it is a monoid in this category of families. And this is the job of the other half of the mathematical model, which is this generic metatheory proof. So we are making use of initial algebra semantics. And as a recap, for every algebraic data type, you can consider it as the initial algebra for a particular signature endo functor. And in this case, we also have the same situation, even though we are inductively defining families of terms. So you can capture the syntax of a second-order calculus as one of these endo functors, and then algebras for this endo functor are going to be just the co-pairing of the constructors of the signature. So monoid is a simple example. You can also do the same thing with the signature of the simply typed lambda calculus or any other simply typed second-order signature you might think of. And then we have this category of pointed sigma algebras. Pointed just means there is a mapping from variables into terms of the syntax. And the initial such algebra, which we denote by this blackboard T, has the property that for any other pointed sigma algebra, i.e. a family A with an algebra and variable map, we have a unique map from T to A such that this diagram commutes. These are the homomorphism conditions. So first of all, it preserves the algebra structure and also it preserves variables. The other way to read this is to think about, if I were to define the SEM map by recursion on the syntax, I would say, well, if I'm in a constructor, then I would be applying this part of the definition. If I'm looking at a variable, then I would be applying this part of the definition. So here, these really capture the recursive nature of the map SEM in this algebraic form. Initial algebra semantics isn't really just about semantics, and this is what we exploit in the library as well. So syntactic operations such as renaming and substitution can themselves be brought into the form of a map from T to A by choosing A to be either box T or this internal hom. That was really the point of our formalism, is to get these into the form of these family maps out of the syntax terms. So that means if I just show with a quite general property that the endpoints of these maps are pointed sigma algebras, then I have induced a map automatically. And very similarly, and this is something that is quite not really seen in practice before, we can also use the same initiality condition to prove the correctness of these maps as well. So, for example, the coalgebra laws for the renaming operation, they are also of the form two maps going from T into some sort of sigma algebra. So to show that these diagrams commute, it is sufficient to show that the edges of the diagrams are homomorphisms of algebras. And by uniqueness, that means they both must equal the unique homomorphic map from T to the other endpoint. So altogether, the initiality proof is a very general categorical reasoning, categorical argument, where instead of doing some sort of improvised ad hoc equational laws, we are really just doing diagram chasing proofs. And some of the steps are really quite non-trivial if you just look at the equational proof, but become quite natural conditions when looking at the diagrams. So altogether, remember, we have not even fixed a syntax yet, and we have not fixed a representation of the syntax. We just prove that if this category of algebras has an initial object, then it has a substitution structure. So to make use of the generic meta theory, we have a script which essentially generates the data type of the syntax and the initiality proof from a quite convenient syntax description language. So here we have a description of the simply type lambda calculus. And from this, we have a script which generates the type and term syntax in this intrinsic form, and also the operator symbols, which are essentially just a list of the operators with the type variables that appear in them, together with a signature which maps each operator to the output type and the input type and its binds as well. So the way this is used is to define the signature endo functor on families. And this is the definition, but really you can think of this as triples of the operator symbol, a proof that the output of the operator symbol corresponds to the thing that is the type we are looking at, and then a tuple of the arguments, which are or must be of the form of the arities of the constructor. And then once we have this concrete definition of the endo functor, we know that pointed algebras for this will carry the syntactic structure, and the initial such algebra will furthermore have the substitution structure exactly by the meta theory proof we proved abstractly. So given this data type terms, proving, or not even proving, but constructing the initiality proof is really quite simple because it is just the trivial recursive definition into a algebra. So these are the only recursive definitions that appear in the library, and you don't even need to write them yourself because they get generated automatically for you. So the semantic map just recurses into the sub-expressions and combines them with the algebra map. And the uniqueness just inductively rewrites the sub-expressions and uses the homomorphism conditions of this arbitrary new homomorphism G. So to see everything in use, we can just instantiate the meta theory with the signature and the semantic maps and the uniqueness proof and do many other things. For example, we can give the environment model of the lambda calculus just by showing that the output is going to be a sigma algebra, which is here is truncated, but it's not a very complicated proof. And that immediately gives us things like the substitution operation, which we have just accessed for free, and also the substitution lemma, which is also another thing which takes quite a while to prove. But in this case, it is given to you for free because it is just a homomorphism condition for the monoid multiplication. And proving the soundness of this kind of call by name reduction system really takes not that much effort because most of the interesting parts are already generated for you. So you can really just go from tweaking the language, adding new constructors, and maybe modifying existing constructors into working on the valuable meta theory in a couple of seconds, the time it takes to generate the Agda formalization. As a more extended example, which also features the second order extensions of our library, consider the syntax of first order logic. So in syntax description files, alongside the type and term declarations, you can also give lists of equational laws which these operators must satisfy. So for example, I can say that the AND operator has to be commutative and idempotent, or I can also just spell out these conditions explicitly and say that for every A and B, the De Morgan law holds. So not A and B is the same thing as not A or not B. And more interestingly, these are not just variables, they are metavariables. And furthermore, they are parameterized metavariables, which means they can take arguments, if you will. So in this law, which states that conjunction can be pushed into a universal quantification, P here is just a proposition, but Q is a predicate because it takes a natural number as a parameter. So when I explain that P and for all x, Qx is on one side of the equation, then I'm instantiating the parameter of Q with this variable that I quantify over. And then I say that that can be commuted with the universal quantification being on the outside. So once I put this into the script, it first of all generates the data type, as expected, but it also generates a inductive list of axioms, equational axioms, using some special terms which are generated together with the syntax constructors, which are the metavariables. So the commutativity law, for example, states that for every two metavariables of sort star, in this case, we can commute them around. And in the last law, we can see that we can expect this to have a parameter of natural numbers and refer to this parameter inside the metavariable via just a normal De Bruijn index. And with a couple of helpful kind of combinators, which make use of a so-called metasubstitution operation to instantiate these metavariables with actual terms, which is defined using things like weakening a substitution, so it's the existing syntactic structure of the syntax. We can do proofs such as pushing conjunction under universal quantification from the other side by deriving it from the existing axioms. So for example, this is an equational proof which starts with commuting these two conjuncts around by instantiating the for all C axiom with A instantiated with for all A x and B instantiated with B. This will swap them around, then apply the other axiom which pushes this conjunction into a universal quantification. And then we can even use this combinator to go into a sub-expression of the expression and apply rewrite rule within a sub-expression. So we state that we apply the rewrite rule in the context, in the whole of this for all quantifier, and we just swap around via commutativity. So this gives rise to a second-order equation reasoning framework in the library with little extra effort on the part of the user. So to summarize, we really have found that the signature of a syntax captures everything you might want to know and prove as boilerplate, but you don't need to do this manually anymore. By looking at everything from the point of view of category theory, helped us uncover a lot of the interesting structure and generalizations of things that appear in literature quite a lot and explain lots of these ad hoc properties that we see a lot. And also a nice perk of this was that existing extensions of the theory, which have appeared in literature many years ago, can be quite neatly implemented in practice as well. So hopefully we have shown that you can have generality, practicality, and efficiency together. Thank you very much.
Okay, let's give thanks to the speaker. So I see lots of interesting, lots of people asking questions online. Let me take one online, one local, and etc. Okay, so the first question online is, why did you use a script to generate the syntax data types instead of using a single definition of abstract binding trees?
So I suspect this means to have like a data type which captures the initial algebra for the ender functor. I'm not sure if I can interact with the question asker. The reason we tried many different options, it really was just the notion of practicality. I'd rather work with actual constructors rather than kind of encoding them in this not necessarily hacky way, but maybe less convenient way using the ender functor options. But both of them work, but you might as well generate the code as well because it's easy enough to do.
Okay, thank you. Any local questions? Now let me take the next one. Are there limitations to the kind of syntax your library can handle?
There are limitations. It does work with any simply typed second-order syntax. So this captures quite a lot of existing syntaxes already. But because it's tied in quite closely with the mathematics, you cannot just extend it to things like dual contexts or linearity easily. This is definitely on the cards, and we hope to turn this into a very comprehensive system which can handle polymorphism, for example, linearity, and many other kinds of syntaxes as well.
Thank you. And the next, any local? I didn't see any. Okay. The next one, the presentation of the substitution monoidal structure in terms of the internal harm, internal harm instead of the tensor product is very interesting. Did you do this because of it worked better in your formalization, or are there any reasons to avoid the tensor?
Yes, so the tensor product is used in the kind of the original pre-sheaf model. Translating the pre-sheaf model directly into a proof assistant is quite tricky, not just because it immediately becomes a very large and complex formalization, but there are some technical issues to do with having to, for example, avoid quotient types, which is something we wanted to do. So instead, by translating this monoidal structure, closed structure, the proofs do become a lot easier because instead of parameterized initiality, you work with normal initiality. And sorry, the question. Yeah, yes. So, and it just avoided some really small technical issues, which kind of the standard skew-monoidal proofs that exist in literature have suffered from slightly.
Okay, thank you. And I think I'm going to take two more. I see lots of questions, but I think we need to take some of the questions offline. So the next one is a comparison with the auto subs will be welcome. The tip, okay, I did not really give one. Do you have anything that you want to comment on it?
Yes, so there are, of course, lots of these different systems. Lots of them exist for Coq and a couple for Agda as well. I think, if I remember correctly, I might be confusing the syntaxes. I think what AutoSubs does is it generates the entire meta theory for the syntax already, which does sometimes result in like thousands of lines of Coq code. We try to keep that kind of, I guess, untrusted generation part of the system quite small. So really, we just generate a couple of lines of code, Agda code, for every constructor. And it becomes a very compact formalization because instead of generating all of these associativity laws in Python, really, you just do that in Agda, and that's more trustable, I hope, than Python.
Okay, thank you. Any local questions? Wow, you have been very shy. Okay, I'm going to take one more online question, and I'm going to switch to I believe we have solved the technical problem, hopefully, fingers crossed. All right, so last question. I love this work, but I also see languages that are other than Agda. What effort will be involved in porting it to my other languages now that you have done this work?
I don't think there is anything too Agda specific other than obviously generating Agda code. You wouldn't really be able to run it in Coq. But it is a formalization which should work in other libraries as well. And it really doesn't make use of very significant like category theory either. So really what we just use is the Agda categories library, use the notion of a category there and a functor and initial objects, and that's it. So it's hopefully quite a lightweight project and can be implemented into, adopted into other systems as well.
Okay, thank you. I encourage the discussion even after the talk, but now, in the interest of time, let's switch to the talk that was scheduled as the first of, but it was swapped due to the technical difficulties.
Thank you.
Yeah, let's thank the speaker again.